font size okay. So we are initializing this object, this dynamic block, with the matrix of the system dynamics, with the control matrix, with the initial position and velocity, and the timestamp. Here we are creating the state vector. The constants are saved in the values of the class internal. And this function over here is the system dynamics. It basically does the matrix multiplication. So here we get the x dot vector, which is the time derivative of the state vector at a given instant in time. So with this sign we perform matrix multiplication, and it's the equation of the linear system just written in Python. And the integration is done in the same way we have discussed. So instead of equating ux to the previous plus some addition, we just do plus equals. So that's the same stuff. We're multiplying, informally speaking, the momentary velocity by dt and adding that to the state, and that's it. And here's the simulation loop. Create the object, and for a given number of episodes, we perform the following. First, we get the state of the system. Second, we synthesize the control, given the number of the step, simulation step, and the current state of the system. After that, we obtain the vector of the system dynamics, and finally, we integrate our simulation, and we just do it in loop, and the system gets propagated in time. And this is just for visualizing stuff. So if we run the next cell, we'll see something like this. What is that actually? It's the simulation of the system under this control, sign control. This control completely ignores the state, and it just outputs a value of the force that is proportional to 20 times sine of number of the tick divided by 8. So no meaning behind that except for sanity check of the system behavior. This control is not going to stabilize anything. We're just applying the force according to the sine law, and that's it. So if we simulate that for, let's simulate it for 300 episodes. Run it again. And here are some plots. Let's take a look. This is the plot of the position over time, plot of the velocity over time, the control signal over time, and this is the trajectory of the system on the plane of the position and velocity as an axis. So if we were applying a stabilizing controller, we will see some kind of approach of the zero position on the plane. Here we don't see anything like this because the controller is a dynamic plug, and it doesn't make any sense if you want to stabilize the system. But anyways, we're just checking that everything behaves properly. This is fine. Okay. And here's the animation. It takes its time, I should say, because it's done in manually, and it's not that fast. Personally, I prefer OpenCV, but here it's not available. I mean, conveniently in Colab. The good thing about Colab is that it's cross-platform. You can use basically any browser to work with this code. But we can do the same with locally. And here we can run this animation. the trajectories were already saved here, so just passing the trajectories to the animation function, and we can run the animation. So what happens is this block is moving something like this. And next up we're approaching the section where you will have to do some coding. We were discussing the continuous version yesterday, and the discrete version here. We're using the discrete version, discretized version, and we can assess each of the state action trajectories in terms of their cost. What is the state action trajectory? It's the combination of states and actions for each moment in time. So we have a number of discrete steps, 300 in our case, and this trajectory costs us something in terms of the control, joules of energy maybe, and in terms of the state. So if we're trying to approach a certain point and we are very far from it, the cost will be high, and the other way around. I propose to use, and this is the standard way of doing so, I propose to use the quadratic cost function that could be set like this. So it's a sum from the 0 moment in time until the last moment of these squared states and actions. Squared in the sense of vectors. So Q and R are two matrices of the proper dimensions. This matrix has the dimensions of the state length by state length, and this matrix R has the dimensions of control vector length by control vector length. We square them, we get two scalars, we multiply these scalars by the dt for current period of time, and we sum it up through the whole trajectory. That's it. So here in this function, we can implement that. Let's examine what's going on. So we get the trajectory, we get the weight matrices, the cost matrices. Later on, we'll see that with them we can balance the behavior of the controller. We can set if we care more about saving energy in terms of the control or stabilizing the system faster. And here we have the x vector, just reformulated for convenience, and the control vector. So here we can write the formula or the code for the cost for a given instant in time, and in this loop it will be summed up here into the final cost, which will be the cost of our trajectory. After we do that, we can evaluate the trajectory that we have obtained in the simulation. So please complete the code, and if something is not clear, let's discuss that.
Sorry, can you say what's R again and what's X vector?
Yeah, so X sub I here is the state vector on this step I. Q is a matrix of size n by n, which is the weight matrix.
What's R?
R is it's basically the same, but it's the weight matrix for the controls. clear what to do or not really? Hmm?
Is it clear?
Okay. So the intuition is that we have written down the trajectory of the simulation in order to understand how good or bad this trajectory is. This exact trajectory will be great or bad in terms of the cost because we're not stabilizing anything really. And the ones that we will get later will be better and better. We'll try the PD control, later on we'll derive the optimal control in a sense. We'll derive it for continuous case with infinite horizon, and then we'll break both of these assumptions. As far as we acknowledge that it's fine. You are completing the code for the state action trajectory. Quadratic. Okay, so who is okay. Is the weight matrix. So there's, first of all, from my side, I'm totally pro that. Second,
Give us the up-to-date name of the first
you want to attend that?
by code. And نحن
You're able to attend anything.
Because yesterday you told me you had it, so now I came today.
It's supposed to be a cost, like a number.
So I have to talk to you.
If you want this formal,
Yeah, this
if you have yes,
it's just it's
Because you're adding them, like they will come out as storage. They are
I might be doing something wrong. The reason why I say it should be one number is because it's like it's a cost.
But it's a
Overall, it's taking.
It's a trajectory. It should
Yeah,
be.
for the entire trajectory, it should have. Cost.
Because we also
You have this, so you have to. Excellent. Yeah, you're doing that transpose times plus transpose times R times That's cool. It should be wrong. Wait, for a second it is that's it. Yeah,
So I put the rest of it in bracket. Anything times to use, I don't know what counts as.
Same issue as you to multiply by all of it. We read, we add, and then another add.
You have a section.
that's it.
Add, we read.
Yeah, so
Like if you look at the equations there,
this equation.
I can just put this up. We're going to act. I mean, of course.
Yeah, it works now. It was working now. It just worked for me. It started
it's for assessing the state action and trajectory in terms of cost.
It's a big change now. And cost, it's the total cost. We're starting with zero. Yes, so every so what is some for example,
That's good.
like when they do like
Basically,
some
just
like
try the formula again.
let's say how would I do summation of I?
Okay, the transpose.
You start with some variable cost.
I don't know why.
J and then do some I. You will start with cost like 2n for I range. Yeah, 0 to n. Right. Then I current cost.
Okay, quiz done.
We already have
the
it.
ending of chapter two.
So we don't need to write the code. We don't need to write the code now.
That's good.
We just need to do
The ground is good. This is us.
X.
Direction of there.
But smart because we make it.
Q. Because the fact is
Here's a max. There's two maxes. There's like a max.
this is the first one.
Oh, the no, that's because they discriminate.
Actually, I'm not gonna. It's good. It's being real.
Plus
It might be for another
U
video.
back transpose of U back times U back. And then all of that we discussed this.
Okay, so let's discuss what's going on. Just a quick reminder, we're talking about
We already have X.
such a system. Those markers are just this. So when we have a one-dimensional block with mass that we can exert force onto, and we want to drive this block along one dimension to 0 and stop it there with 0 velocity, prefer, ideal. Let's suppose that we do something that makes sense in a way, and the trajectory looks, or the position by time looks something like this. We start in the negative coordinate here, then let's suppose we waited for some time, then we started accelerating in the proper direction. Now we come to 0, we overshoot slightly because of the inertia, and then we kind of stabilize the coordinate. So this is an example of a trajectory that you can think of if you're trying to stabilize this block with mass. The plot of the velocity will look something like this. Okay, so in the beginning it's 0, 0, 0, 0, 0. It's increasing. Then it's decreasing, it's negative here. So just the derivative, right? Some kind of the plot of the velocity. And the control will be yet another plot. First we started applying control to the right, then to the left, the second derivative, you can say. Because the only force acting on the block is the force that we apply. And the question that we're trying to answer is how good or bad this trajectory is. So these two things, they compose a state trajectory. And this composes the action trajectory. If we are running this simulation for n, big N, number of steps, our state action trajectory is the following thing: x or p, I will call it p position. the state action trajectory, states and actions, and more specifically, positions, velocities, forces. Yep. Is this clear? So for each moment in time, we have the position, the velocity, and the force that we apply our control. That's it. And what we want to do is we want to derive, or it's better to say state, formulate some kind of a cost for each of the moments in time, so that we can sum this up into a single cost of the whole trajectory. So the cost of the whole trajectory will be the sum of costs for each moment in time, right? Some kind of a function from of x sub I, u sub I. Please give me feedback if it's clear or not. And you can keep doing that all the time, so it will be better. I will understand the situation better. So, what this cost should represent is how good or bad the trajectory is. If our position is 0, this momentarily cost should be equal to 0, where we have already arrived. That's good enough. If, well, I mean the part that corresponds to the position. The same for velocity, and the same for control. If we're not applying any control, we're not using any energy from the battery or a gasoline, you know, the control cost is 0 if we're not applying any control. And a convenient way of setting this kind of a cost is a quadratic cost. Why is that? Because with quadratic cost, it does not make a difference if the deviation from 0 is positive or negative. It's the first. And the second, the quadratic functions are really convenient to analyze. So if we want to minimize something, we can formulate in advance the minimization problem quadratically, so that later on it will be convenient for us. So we're going to set this cost in the following form. It will be x sub I transpose. It's a vector multiplied by a matrix multiplied by x sub I plus u sub I transpose R matrix is another matrix u sub I. And actually we have to require something from these matrices. Let's take a look at them. So Q is a matrix that is multiplied by the x vector from both sides. Remember that x vectors live in Rn, the u vectors live in Rm. So this Q matrix has to be of dimensions n times n. And the R matrix is from the space of the matrices m by m. And also we have to require a couple of properties. We want the matrix Q to be positive semi-definite, and matrix R to be strictly positive definite. Why is that? Because here we require any control for us to cost something. With this, we're stating that no control is could be performed for free. We're still spending some energy. Even if we are pushing this mass just slightly, we still spend some energy. And this property is needed to assure that there is no such state other than zero. There is no such state where we can decrease the cost. So imagine there's I want to stabilize to that certain point, and there's a point here where I stay and minimize the cost at the same time. So the cost regarding the state should never be negative. Otherwise, I would stay somewhere outside of the destination point and decrease the cost. That will not make sense. So getting back to the code, what happens is we are working on this exact function, on this exact part of the function, because this sum is the loop that was written in advance, and before and after this part, you see the comments, hashtag your code below, hashtag your code above. So this is the only thing you need to do, and the vectors x sub I and u sub I are already there, so we only have to complete the formula. We have to write this in terms of the Python code. If something is not clear, that's my fault. Tell me.
Why do we transpose?
Why do we transpose? Because imagine that we have multiplied this vector by this matrix. As a result, we'll get a vector. So this is the matrix, and this is the vector. If we multiply them, we'll get just a vector. So if we do not transpose, we will multiply. We'll try to multiply this vector, not transpose x sub I, but the result of the multiplication, and they cannot be multiplied as matrices. So what we do instead is we transpose the state vector, multiply it by the matrix, and multiply it by itself. So here we get the column, we multiply them, and get a scalar. So this is a scalar, just a number, and this is a scalar as well. And it means that the cost of each step is just a value, a number. We can sum them up, and it will get, it will give us a value, a single value, of the cost of the whole trajectory.
Yes, you mentioned that Q and R are semi-definite. What does it mean?
Positive semi-definite means that for any vector, its square in terms of the Q matrix will be not smaller than 0. So basically these matrices Q and R are the matrices that set the weights properly. If we would omit these matrices, this will be just the scalar product of the vector by itself. So it's sum of the squares of all the entries of the vector. And with these matrices we can regulate the weights. The simplest case of these matrices is them being diagonal. So we can set the weights something like this. With zeros everywhere else. And in such a case, this multiplication will give us the following. It's the weight u sub 1 and the first component. So I, the component number, okay, let it be here. Oh, sorry. Yeah, the first component. Left upper subindex, but it's just the number.
So when you say q greater than or equal to 0, what we actually mean is that when we evaluate x transpose times q times x, that should always be positive.
You mean about the property of being positive semi-definite?
Yeah, so like for, is that what we mean? When we say it's positive semi-definite, we mean that take any vector.
Yes, it's for all the vectors. All the vectors.
Okay.
This multiplication will be non-negative, which means that we cannot be somewhere outside of the origin. Yes. And for the diagonal form of the matrix, which will this multiplication will look like this. And here we'll have u sub n squared x sub I squared the element number n. Is this clear? No, it's not. Okay, so what is not clear? Tell me what is confusing here. Which step exactly? So until when it is fine, and since when it is not?
In x, in the equation you just wrote, so the 9, 1 is from q, right?
9, but where?
In the equation you were writing.
Q.
Yeah, the 9.
It's not 9, it's q.
Oh, that's q? Sorry, okay. q1, that comes under
Yes.
the matrix.
The Q matrix here is this one, just the diagonal matrix.
Yeah.
Q1, Q2, 1, Qn.
Okay.
And we take the x vector. So it's the first component, x sub I, second component, x sub I, and the component. This is the vector. We multiply it by this diagonal matrix, and then by the same vector.
So where is the transpose vector in this?
Transpose? Here.
Yeah.
So this thing is equivalent to the following.
Oh, okay. Is that why it's like you square it? Like x is squared?
Yeah, so here, if we multiply this vector by this matrix, we'll just get the vector that will be weighted with these weights.
Okay, so it'll be like q1 and then x squared.
Yes. So let's see. X 1, x n, and here we will get call the vector q1, x1, q n, x n. Well, and finally we multiply them, and they get multiplied like matrices do, and we get exactly this.
Okay, got it. Yeah.
So it's fine now. Or not really. Wake up, tell me something is not clear. Fine, okay, awesome.
It's a matrix, right?
Q, yes.
Yeah.
Yes, it's n by n.
What's this
R is the matrix of the weights for the control. So it's basically the same but different dimensions. And it's strictly positive definite, so here we'll have just the strict inequalities.
The x is for position or the state vector, is that what it is?
Here, you mean in the definition?
Yeah, x and then
Yes.
and on
Yes,
top.
yes. For all the state vectors, this property holds.
Okay, and then that's for u is control vector.
Yes, use the control vector.
And so q and r are the weighted matrix for each.
Yes, yes. Q for state.
We got a value of 4,800, so what does that mean? Like, what is the value?
What does the value mean? It's a good question. So let's imagine that we have got some kind of trajectory here. Here we can use the units of, say, meters. So now we are in, I don't know, 7 meters off from the desired position. How bad is that? And in order for this summation to make sense, they have to be measured in the same units, right? So these matrices will have their own units. This is meters. This is okay. So the first entry of x is meters, right? And here we have, let's say, joules of energy, or watts of power at an instant. So let's take a look. We can consider the first entry of the first part of the sum. U sum. Okay, I'll skip this sum for now. Okay, so Q1 x1 squared, and we'll add up to this the rest of the elements here, and then we're going to add here to the same sum according to this formula R sub 1 Q1 squared, and they have to have the same units. So if the control is measured in say watts, this will be some kind of coefficient times 1 squared. So if we spend 2 times, if our power at the moment is 2 times greater, the cost will be 4 times greater. So this value over here, this R, could have the units of, for instance, watts to the power of -2, and then all the units just get vanished, and we get some kind of abstract value, abstract notion of cost. Well, it could not be too easily clear by now. You know what we can do? We can measure this in dirhams. So this control is being transformed by this coefficient to just price. And same for the state. So how can we get intuition about that? Let's consider such a situation. You're driving to KU to the class, and in order to accelerate your car or slow down your car, you have to spend some gas, and you are going to be penalized for being absent from the class at each moment in time, just slightly, and you will be penalized by the government for the speeding, for breaking the speed regulations. So in order for us to sum it up, we have to somehow make this cost uniform. So we do it with the proper weights, with the proper units. It's better, right? So now it's clear, the conception. And so there are certain cases of cheap control and expensive control. If the entries in the Q matrix are very small, we don't really care about getting to the destination very slow. We just want to get there, and on a big time scale, we'll have to do it, but we don't have to do it very rapidly. And if at the same time the values in the R matrix are big enough, we want to spend as little control as possible, or to spend as little energy as possible. So here we can care for energy efficiency. And otherwise, if we have big values in the Q matrix and small values in the R matrix, it means cheap control, like in the competitions with very limited time. We spend a lot of energy and a lot of resources in a very short time span, but this is the costs that we have chosen for us to win the game. So these costs are one of the things that we as control engineers have to specify. following some intuitions and the goals.
So the idea is to be time efficient and energy efficient.
Hmm?
Like you want to be time efficient and energy efficient, or do you just focus on one?
There is always the balance, and the exact balance is defined by you as an engineer while you are setting these matrices. If we want to drive this block to 0 as soon as possible, then we have to set this value big enough. How could I? Okay, big value, and the value that will correspond to the speed will be small. So what will happen is that we will very rapidly approach 0 in terms of the position, and will oscillate here for some time. And the velocity will be relatively high, but the square of the deviation by position will be very small. And otherwise, if we don't really care that much about the position, we set this value to be slow or to be small, and the velocity, we are weighting it so that we are getting penalized very much for breaking the speed constraints.
Okay, so if you like really want to get to the position fast, but don't care about the speed and like we don't mind oscillating so much, we can just set a really high value, for example, like in that first row first column, like
Yes.
first position, or like force, for example, in the R matrix, we would just like if we have a problem applying a lot of force, like we want to minimize the control that we apply. We would say, for example, 2 per unit or like 100 per unit, because we really don't want to apply much control. And then we get to get the values for k accordingly, like we get to. So we're trying to minimize the cost accordingly based on the.
Almost, we're almost there. So, what do I mean by setting different values for the cost? The point here is not to minimize cost per se, but today we're going to get to the derivation for the control that will indeed minimize this cost. So we are setting this cost accordingly to the problem, and then we're going to get the general case, a function that will give us optimal control according to that cost. So if we first use the proper intuitions about not applying too much force or going to the origin fast enough, and then we'll perform this minimization, will be effective.
There's no like set value for optimal control. The value depends on the case. Like you might say around 4,000 is optimal control value.
The optimal control is optimal control there is a function in this case that is defined in terms of the weight matrices. So yes, it directly depends on that. It's the only thing that that defines the optimal control is the cost that we're trying to minimize. And are there any questions anymore? So it's fine. Okay, with this in mind, let us complete the code snippet. This one.
Sorry, what is W?
W. Yes, those are the units. They're confusing. So I was providing an example. What could be the units here? But never mind. We have already discussed that. So just this formula. And if you check the code, the matrices Q and R are probably identity matrices, because here we don't have any specific considerations about minimizing this and that. We're just trying things out. By now, if you were working with some kind of, in the context of a computation, then you will have to find out the proper values depending on the system, on the environment. But for now, those are just some convenient matrices.
But Q1, Q2, and all of those Qs be the same value?
No, they could be, generally they could be different, like in this case.
Like
dt.
why are we multiplying by? Like,
So
why are we integrating?
What is dt in the code? dt in the code is
It's the time step, yes.
Yes, this thing. And
Why not just sum the cost like at the point? Why like
why not just sum? Well,
Why not just sum?
we can do that, but let me explain. So imagine that this is the plot of the position. What we are doing with this kind of summation? I forgot it here. Here. Or delta is better to say. So what do we do now is first we square this value according to the Q matrix, and after that we have to multiply it by dt, because if we change dt 2 times, it's better for the cost to stay approximately the same way. So depending on the dt, it is more rough or more close to the situation.
that value for the short duration.
Yeah, so we can change it for the dt, and we're expecting the whole cost to be in the same order.
Okay.
And we're kind of numerically integrating the cost like this.
Once you get this cost, how can you use it?
We can compare controllers. So imagine you and me have created two different controllers. We're going to compare them, and I get the cost of 300, and you get the cost of 200. Then your controller is better.
So the closer to zero, the better.
The cost equal to zero is not always possible, because if you're outside of the destination, you will have to do something. So cost of zero is usually not attainable, but less is better, yes. And today we're going to derive exactly the specific way of getting to the minimal cost possible.
So this cost is like a performance measure.
Yes. Or the cost. Performance, better performance, higher performance is better, and lower cost is better. Otherwise, other way around. We want to minimize the cost. So can we complete the code now? Okay, let's do that. This thing is a scale. So it's a value already. Okay.
It's taking this and this first value of this and this one, and they keep on clumping that into your backend. So this is x.
Yes, because this is a value already.
Because the transpose and
Yes. There could be some problems if
I'm just
you for care about
that's how you do program.
being outside of the design position with the high velocity, you can have the there are many diagrams because want to minimize the position and the cost of the event. If there is some dependencies here, something complicated, you can set that and microstructure.
No, so you do apply. When you do apply,
Again,
this is something
we did,
when
State actual
zero
the whole cost of the whole check.
So this first is like this.
The sum of those things that you have.
This first is anything you put, if I put one comma. Let's say I find out array. This inner list, this.
Exactly. Yes.
This outer list is this. Okay. This inner list is this. So if I put like instead like this, like 1 comma 3 comma it'll be 1 comma 2 3 comma 0. This is a matrix. If I do
The exact value of an array could only tell you something bracket if there is a kind of intuition behind the settings.
closest bracket comma another bracket
This has
is,
one column.
yeah, one and then 2 rows.
We're here and
So this is XTR.
is that position just 1 meter.
It's down. Okay.
Yeah, it's a stack. No. So you have this is X vector. This X vector will be X vector equal to yeah, it's just
We're not moving, but still
yeah,
it's supposed to be. You can compare your cost with the cost of
Yeah.
doing nothing or doing.
now when they do so what we're trying to do with the cost, current
This
cost.
is very simple calculation. That's exactly
Equals to X vector transpose, so like XTR
is increasing. This value is present back because
Okay, forget X vector.
yeah, later we'll get much better.
I also consider that. X transpose
It's probably something related.
means
Plus,
no plus. So doing this part. Pronouncing.
transpose. Transpose. Oh, you that's my bad.
So I was just gonna-
That's my bad. So X vector is this. So when you transpose it, it's like this.
Yeah, so,
Do you know what transpose is?
yeah. So I was doing the
You can't do it all. So Q is given in the function. So we have put in whatever Q is something for Q for free.
X1, X2,
X1 is a
aren't
single.
we supposed to have one per okay.
That so okay, Q is X1 I X2 I. This X1 I is just position B I. X2 I is just dot I. This 2 is just this is just B. It's just why is he doing this? Good question. So in our simple example, we just have like a second example. This X vector. It's just equal to B and B. If we have more complicated example, for example, X vector is equal to transposes, we have more degrees of freedom. We not data. So that's why he just writing as like general X1. So So whatever this first thing is, second thing is second.
Yeah.
It's just because
That's why one is position, the other one is velocity.
yeah, Q1 is for precision, Q2 is for velocity.
This is what the example is.
Why do we need data whenever we meet? Whenever I feel like it's anyways, okay. This is exact same. Someone said,
That's why I'm not
deja vu. That's what I want to do. I just had deja vu. I did
Got it, got it. I got it.
That's what the first one.
Maybe not this.
I feel like I did this exact same.
Was it when you were trying out?
Possibly. Yeah, when I was messing around, I was doing this exact same.
Template into which we can
So, once you
put
go
the
into
data
you get
for
the second
different
example, the
instances
second.
of the
The second, I would add, so P0, P, the root gives you an instance of the
Yeah.
P0, P1.
These will be until the number of like
Yeah.
yeah. So here we
This is just how you write it.
also technically N and
this is the new type. So it's like chart, this is the new type.
because as that
Integer is initialized with just the value, and this value is initialized with some of the values.
and that it is
So now we have a more.
We could keep n small, but then our key would be really active. Like,
yeah
you
because
are
the
short.
delta here will be
Yeah.
So we can create two blocks.
Yeah.
yeah
We can create
yeah
an instance of this
It's just a thing.
piece of for each there will be a space
Yeah.
and your U is a control function. If your
So, okay, let's talk about unit first. In our case, we just use like a single. So we can use an individual apply control data. Let's say if we can apply a force that should be R would be like yes, so R1, R2.
this will depend on the force this one.
Yeah, this is the cost for the force. This is
Amazing. Okay. It's like
if you want to understand the quantification of what I explained, it's possible. I think I explained it.
I did. We should I guess
with some
And then he'll write after that.
Thank you. Much appreciated.
these are the
I get
Try doing it. Like the code part, you get it, but you just think like, whatever this is. See if you get it. Especially the one.
we have written instruction in code. So first this function and then code function. Who has completed this part? Okay, try finding someone who did not. This is good.
Everything you were doing in the second half, you were doing.
Have to first try.
Let me explain it to you. I would love to, but
No, but
Yeah. All of you because like
I will check in the play.
Okay. You can just
Maybe I will go for it now. Because it's but also
start on the first one, then the language will be important.
Yes, yes. That's what I didn't sleep yesterday. I get it to sleep. I came back pretty
Yesterday I tried to
in these lectures, but I stopped it. They're kind of the same, right?
say in terms of the content.
Yeah.
The thing I was discussing yesterday were pretty much covered, but yesterday we had live feedback. In terms of the computer vision, it is completely covered on static programming. Yes, it is covered completely in great detail during this internship.
So yesterday's lectures,
It's covered it's there.
to see what I missed.
Yes.
And next week we'll start laboratory stuff.
Yes, so the first 2 days is the 8th.
There is actually, I really want to remember, they sent an email out.
On Wednesday there will be
So we have, so Friday we'll attend, but then Monday and Tuesday are off.
yes, on Wednesday there's a second student further, so it will be somewhere in Dubai. Someone else will give a lecture online. And on
Wednesday so far. Wednesday so far.
Wednesday is like yes, most probably 95%. And Thursday and Friday, so that here in person he'll be talking about more practice related stuff. Or to something about but anyways, during the next 3 weeks, the plan is to spend the majority of the time on practice.
How do you comment the
I'll do my best. It is right.
Some students as well, I noticed on WhatsApp, they kept attending Slovenian traveling or something like that.
Yeah.
Basically, you are like waiting for the actual application.
Thank you very much.
Can be like there's a correlation between X and Y of values. They could technically be so they could like change it but diagonal matrices that is here because they can so each one is only one value.
Is it a case where the course wouldn't be a diagonal?
Yes. If at the same time, if you at the same time care about being all the position and grow the kind of then this will be here the position, you have to very much.
force doesn't multiply with the.
Yeah. Yes.
We change the value. Check your number.
Would it be still a scalar even if it's but this property would hold. This property will hold, but this property. Even if it's all positive numbers. If it's all positive numbers, like you make it be greater than or equal to 0 for let's but if x is negative. If x on x. That's right. I think I get it. No, yeah, no, I think I get why. It's because x can still be negative. Okay. This method happens after it's multiplied. So when it's multiplied by this, like when it's multiplied by any value of x, we get some negative number here.
So when we multiply,
She's doing the math.
Like,
yeah, so she's wondering what will be
let's say that's like, I can like before multiplying the times. Before square. Can still be negative. Like, you can have a negative value here. This one is. And then if you multiply with this, say no, it can still be negative because this won't hold true. Okay. Okay, what's this example? I can't take a specific example, but it's definitely. I understood. It's not what let's do it.
Sometimes you have a sample, sometimes this will be other things.
Yeah, exactly. If you change R, your control vector will use that vector. To get to the point. Yes, yes, yes. Because R is being written right? So it's obviously effective.
Always be positive.
If we change Q to make it better, we will optimize the time. So when we reach the position faster, so it'll be the overtop of the sine graph or the but I'm trying
If I'm not mistaken, about this, is that what I'm pretty sure?
The dimension?
Yeah, let's have this whole lunch.
Yeah, this
It's called a conference. It's
'cause so we have matrices have right, so in any vector space, matrices can have a lot of yes. What are you talking about? No, that would be.
Yes, it's saying you're right. Well, this problem. One space to which one is still this space. Yes, it's setting a very this is also the attention back then. This is not exactly the case. This is one of the case. We don't have the bias, so we don't have they only change the effect of the vectors, right? Or not. So
Once you have the ideal value, how do you add the ideal vector?
that's slightly different topic. So what this says is that if you take a specific ideal vector, the second ideal vector,
Yeah. Once you find the ideal vector, right, after the transformation, you always scale graph. What is this
That's what I did. It's like you get to eat like I look at the vegetables.
or of the one that's
Yeah,
this one.
yeah.
Okay. And the second thing. And That's if we have any negative eigenvalues, this alternative is delivered not positive sign. And this case is because the matter is just calling friend.
Exactly. So going back to the equation for 10-3, so here we're analyzing what is happening.
We're analyzing A
Here we're just analyzing the code.
we are wrong, so the same is both
Okay. So if you're wrong in both the position and the velocity at the same time, analyze the code.
I think that's it means that he either puts it on or something like
Okay, so let us proceed. I don't know what happened to the internet, but for some reason,
It is working in the morning.
okay. I think let's get back to 1 p.m. Hope that the internet will start working, and we'll do the derivation of linear quadratic regulator.
The favorite derivation.
I think that will take us the whole 2 hours, maybe slightly longer.